talking here, and maybe a little more about what I've done before. So I used to do a lot of open source. I've worked on developing platforms pretty much since I started working. All kind of platform, financial, publications, green tech, all sort of different projects, insurance. And then I was, I said, involved a lot in open source. So I went to the Apache Software Foundation is one of the few open source foundation that's still really active, and they do a lot of great stuff for open source in general and support. Because a lot of people think that open source is just pushing some code on GitHub, but really it's not. It's about the community, the governance, the process, the law you have to do with copyright and licenses and patents, and so it gets really messy, and it gets kind of risky too. The Apache Software Foundation exists only because the Apache web server at some point was 70% of the internet, and the people who were working on it started being sued because of issues with that code, and like the site went down, and somebody would lose money, and then they called a lawyer. So that's the use in just 2 minutes of Open Source Software Foundation, but I can tell you they're really useful. There's the Apache Software Foundation, there's Mozilla, there's Eclipse, there's like maybe 6, 7 big ones, all sometimes with affiliations, and then you have all the standard bodies and all that. But from an open source standpoint, I really encourage you to get a little more familiar with those foundations because they're really useful for any coder. So as I was saying, yeah, I built platform for a while. And that's what I'm doing again at Cypher, where we're building a platform for blockchain development. So we support any blockchain, same infrastructure, same source code, everything. So right now we support, as far as blockchain is concerned, Bitcoin, the Bitcoin testnet, Doge, Litecoin. Another coin is called Riou, and we have our own Bitcoin. Well, it's the Bitcoin-like testnet, but we're the only one mining it, and we mine reliably every minute, and that's mostly for development. We have an automated faucet, where you can ask for coins, and so if you run integration tests, it's an easy way to do that and have your transaction confirmed every minute, and so you'll always get coins, always going to get confirmed. So for some tests, it's much easier to play against. So we built from the bottom a full node Bitcoin client. So everything, most of what you've heard, we know pretty well because we coded every single part of it, all the protocols, every single one of the message we just talked about during the previous sessions. And what I'm going to talk about now, which is scripting language, which is also like all the logic between validation, the memory pool, the chain, adding blocks, all of that. And then we offer all of that as a service with APIs that developers can build against. And there's all, I mean, you can just check on our website and the documentation. You'll see all the type of services that we offer: notifications, confidence factor, all of that. So I'm going to go into the Bitcoin scripting language. So it's more applicable than you would think because all the altcoins are just fork of the Bitcoin scripting language. So there's pretty much only one as far as blockchains are concerned in this one. I'll talk toward the end more about alternative and other things that have been built on top. But from a blockchain standpoint, 99.9% of scripts that are getting executed right now as we speak are just that. I'll go into more detail than you probably ever wanted to know about it, but then you will know everything there is to know about it. There will be really, really little left to learn about the scripting language after this, except if you were to implement it yourself, then you will learn all the difficulties behind implementing it, but that's about it. So we'll see, I'll go quickly first about why scripts, what is it for in the first place. Then the scripting language itself, what the characteristics are. It's a programming language. It can be, it's not a general purpose programming language, but it uses a family of programming languages that have been made general purpose. Then we'll go into the detail of what are the main standard scripts that are accepted in the Bitcoin network. And then all the details between every single type of the standard scripts, how they execute, how they run, what do they mean, what are they used for. And then we'll finish with kind of the future kind of thing. So you've probably seen that already, hopefully. That's two transactions that are linked together. One has an output, one has an input that spends that output. The first one on the left has another output that goes to is either unspent or maybe goes to another transaction, we don't know. And the right transaction has also two other inputs besides the link one, where the money comes from another unspent output. A word you often hear is UTXO, or unspent transaction output. A lot in Bitcoin is about knowing what the UTXOs are, because that's basically your working set. That's the transactions that are going to get used. The ones that are already spent and fully spent, the output that have been completely used, are mostly irrelevant except for kind of data mining standpoint or checking past transactions and stuff like that. So the relation we're going to explore a lot in this talk is that line between the output on the left and the input on the right. That's where scripting is, and that's what says whether a transaction can be spent or not. That's the only thing that says whether a transaction can be spent, except like whether it's valid at all, or in which case it's going to be dropped, but it's what guarantees that you have the right to spend that money and make another transaction that transfers that value somewhere else. So, our same scripts are the only thing that allows spending. Whether you can spend that money or no depends on the return value of the script. The script is going to be run. If it returns true, you can spend that money. If it returns false, you cannot spend that money. The output scripts are matched with an input. So in all this talk, when I talk about the output, it's actually the input of the input. So the input references an output. The output is what's getting spent. The input is what's spending it. So the relation goes, the output existed first. The input spend that output and exists after. The input references that input, that output. So again, going back to that diagram, right? The output on the left side exists first. The input spends it. That's pretty crucial to understand, otherwise you'll get confused the whole talk. The input script is usually called the script sig because it usually contains the signatures, which is still mostly true, so that's fine. The output script is called the script pub key because it often contains the pub key, but actually that's not true anymore because it contains the hash of the pub key, which is called an address. And so the script pub key term is now not so accurate anymore, so I will just call it script. And you will have the script and the script sig, which contains mostly the signature in most cases.
Matthieu,
yeah.
In the book, the sort of class book, Mastering Bitcoin, Andreas calls it some really good names, which is locking script and unlocking script.
Oh, okay. So the remark where that Andreas Antonopoulos in his latest book called it the locking and unlocking script, which are good terminology, because on one side you want to lock the money, on the other side you unlock that money. Unfortunately, few people call it that yet, but I'll try to do that. So, in light of that locking, a pair of outputs and inputs in two different transactions is a function invocation. The script in the output, the locking script, you can think of it as a function. It's a hard-coded function in some piece of transaction, but it is like a function. And those functions take parameters. And the parameters are in the script sig. The money can be spent if that function applied to those parameters returns true. So here you have an example. You don't need to look too much yet inside what's in the middle, but basically you have the unlocking script on the left-hand side, the script sig, which are the parameters, the arguments, and the locking script on the right-hand side, which is the function. The parameters apply on the function. If they return true, you can spend the money. And so, yeah, again, just to emphasize, what gets confused is usually this is represented left to right, with the parameter on the left-hand side, and the script on the right-hand side, but the script exists first, that's our output. The parameters or arguments are provided later to unlock that script.
So can you actually go back there one slide? Just to be clear, the script sig is what's the output script?
Right, so the script sig is, the script sig is in the input. That's pending the output.
Very good, that's all I was doing, that's all. I think I was just staring at it wrong, thank you.
Yeah, so like again, if you look at it, the script sig is in here, right? The script itself, the locking script is in here.
Right.
That's what I call the function, and applying the function to do the arguments provided here says whether it can be spent or not.
Great, thank you.
So now let's look at the language. So the Bitcoin language is a stack-based language. There's a pretty long history of stack-based language. One of the most maybe venerable ones is called Forth. So that's one of the early books about Forth. I think it's listed in the, it's number 4 in the worst book covers ever. And it's a book about Forth, you know. So there's a long history of stack-based programming languages. Forth was created in the 70s, but then there's a whole set of history after that. There's Joy. It was used a lot in the 80s for microcomputers because it's really compact, uses very little memory to execute, can be sent around really easily. So all of that made it a really good fit for something like Bitcoin, because that's a script that will be sent around everywhere in the world in every single transaction. Needs to be easy to read, but still needs to be really compact and efficient because a lot of people will be executing. You have to think that every single transaction that's sent, including say 5 inputs, will be executing those 5 inputs on every single full node that exists. So assuming like 5,000 full nodes out there, you have 25,000 script execution for that single transaction. So we'll start with a simple example of a generic stack-based language. No special stack-based language. We use simple instructions. So in a stack-based language, everything's a stack. There's nothing else. It's stack all the way down. You have an instruction stack and a data stack. In that example, the stacks are read from left to right. So the left part is the bottom of the stack, the right part is the top of the stack, and that's execution run after run after run. So what you do is, first you start with an empty data stack, and then you have your instruction stack that's initialized with the instruction you want to execute. So that is what you actually want to execute. So you're just going to run that instruction set, and you go from, actually sorry, that's misleading. That's the top of the stack. So you go from the top of the stack, down the stack, and you pop every single element. So you start with an empty data stack, first element is 3, you put it on the data stack, you pop it from the instruction stack, it's not there anymore. Dup is a duplication instruction, so you end up with twice what's at the top of the stack. It just duplicates the last element. This instruction has been popped out of the stack, it's not there anymore, so next we're going to execute this. Mul is multiplication, simply, so you multiply the 2 last elements on the stack. So you pop the 2 last elements on the data stacks, you multiply them, put the results on the stack. 3 times 3 is 9, that's the next instruction. Then 10 is just a value, you just push the value on the data stack, so you end up with 9 and 10. Min is the minimum. What's the minimum between 9 and 10? It's 9. So the minimum instruction does the same, pops the last 2 elements from the data stack, computes the minimum, put the result on the stack. Then square root of 9 is 3, and you're done. Your data stack is empty, result is 3. So that's a very simple execution logic, right? If you were to implement this, and I would give you any instruction at the top, you can implement that in very, very little amount of code and do it really efficiently. And all you need is 2 stacks. So So the Bitcoin stack language is very, very similar to that. As far as values are concerned, everything is a byte array. So it only manipulates byte arrays that get pushed and popped out of the different stacks. And then instructions are just a single byte. Instructions actually are the thing that give the value their meaning. So depending on the instruction that's coming next, a value can be, again, a byte array, or it can be a boolean, or it can be an int, or it can be, well, actually a number. So here are a few examples. The opneg would calculate the negative value of a number. We'll consider the byte array 30 to 111 as a number. So it will do that by saying, okay, it's 30 to the power, 30 times 256 plus 2011, right? So 30 is the upper value of the number, and 211 is the lower. If you were to use the SHA operation, which is also a standard operation on the Bitcoin scripting, it will calculate the SHA of those two hex byte array values. If you were to take up verify of the byte array 0, it's a boolean. So it really depends on the instructions that are going to consume those values, and that would give you the result. String operations have existed in the language from the start, but have been disabled because there was no really use for it, and then they're all trickier to handle, so then you ended up not being supported. There's conditions, so there's actually a lot of stuff. You can look at the I'm going to go into a fair amount of detail among them, but there's a full list of instruction in the Bitcoin wiki script page. If you just Google Bitcoin scripting language, you'll run into it, and you can see everything. There's a lot of like, stack operations and all sorts of things, but you will not find any loop. That's for good reason, because the scripts are going to be executed on a kind of machine, and if you have a loop, well, you don't really know how long the loop can execute. And if it's based on the condition, it could be executing forever, and you don't want to run that on, you don't want to run an unknown type script on your machine most of the time. There's a few shortcuts to push on stack. So in my example, like earlier, you saw that numbers were pushed directly on the stack. We kind of had the same type of thing where any number between 1 and 75, that's an infer equal, by the way, will push that number of bytes. That's next number of bytes on the stack. And then there's several type of crypto functions that I'll also go into some detail. So all operations are called opcodes. So when I talk about instructions, I'll talk also about opcodes, which are operation codes. It's a terminology that's mostly used in VM implementation, but also in stack-based language and anything that uses a number to represent an instruction. Each operation has a single byte, which makes them really compact. So you just need the byte for each instruction and the data on which those instruction operates, and you're pretty much set. The code is overall kind of smaller, actually, like very small, especially if you compare to languages like Java or something like that. And then they're also often represented as hex. So you will see a lot of hex in that presentation. So AA is the number 170 and is the up hash to 56 instruction. So when you run through a byte array, that's how you will interpret it. So I'm going to run through a few different, like just to give you a little sample. They're not the most interesting thing to see every single instructions, but at least you'll see a good sample of them. If you're so inclined as to write your own script and try them out, not on the main Bitcoin net, but on the testnet or something else, then you can totally do that, and you can have fun with simple, I don't know, additions, or we'll see another script later, but you can make all kind of stuff. So the first is the push operations. So push data 1 will push 1 byte of data, which is supposed to be right after that instruction, onto the data stack. Up 3 will push the number 3. Any number between 1 and 75, that's an infer equal, will push the next n bytes onto the stack. That's how everything, like public keys, signatures, any type of data is pushed onto the stack. And then you have like flow operation. That's actually not used that much, but you see them. Like if then else, return the script right away and say that the script failed. Updrop, updump, upswap are stack operations. So you have you can operate on the main data stack that your script is executing on, but you also have an alternate stack that you can manipulate in Bitcoin. You can do pretty creative things by just manipulating those two stacks, the main data stacks and an alternate one. You have comparisons where there are two things are equal, and there's other like big comparison operators and all sort of things. Arithmetic, so add, less than, max. And then the most interesting part of all, which is all the crypto primitives. So the one unique thing that Bitcoin has and most of the blockchain languages have is they have a fairly complete set of crypto primitives that you can use in your scripts. And some of them have a pretty simple deterministic behavior, like RIPEMD160. So RIPEMD160 is a hash. You probably heard about it before. It's just used in Bitcoin because it's short. A SHA-256 will create a pretty long byte array, whereas RIPEMD160 will just create a hash that's 20 bytes. So those are fairly simple. They just take the data, hash it, and put it back on the stack. Check sig and check multisig, check signatures. And that's kind of the bread and butter of Bitcoin. We'll go into a lot of detail in that. You'll see that checking a signature is actually much harder than what you would think. So the evaluation logic is this, and that's pretty much what I did in my example earlier, just much faster, that's all more explicit. But you start with an empty stack, so an empty data stack. The instruction stack of course, is not empty, it has all your instruction set. But you have an empty data stack to start with, and you start evaluating the script seg. So that's an error. So you start evaluating the script seg, which is the input, right? So the input that is pending. So that's an error. It's not the output to spend, it's the input that is pending the output. So you start with evaluating that part, the script seg, that typically contains a signature but can contain anything, which is also, in my previous example, the argument to the function that is the script. So you start with an empty data stack. You evaluate the script seg by putting it on the instruction stack, running through it, and then you end up with some values in your data stack at the end of this. You reuse that stack, and then this time you execute the script. So the script this time, which is the output to spend, well, the code embedded in the output to spend, and then execute that. Executing that should give you a result whether the whole thing is valid, whether you have the right to spend that transaction, and whether you don't. Whether the parameters that were in the script seg, in the new input, really apply to the function that was embedded in the output. Yeah.
I think when you say like new input, that's brilliant because otherwise my brain gets confused because there's two transactions, there's an old and a new, and saying old and new is better than saying transaction 1 and transaction 2. So keep it up.
Yeah, so the remark was to say old and new is sometimes a little easier because you know what's the new transaction that is spending the old transaction. So you have the new input that is spending the old output.